Welcome back to the next video, everybody. Today's video is on the Zariski tangent space from a functorial point of view. So let's get it. Let lambda be a coefficient ring. Let R be a coefficient lambda algebra. And let's call the maximal ideals of these guys M lambda and MR respectively. The Zariski cotangent space T star R is the maximal ideal M sub R mod its square plus M lambda times R. And what do I mean by M lambda? I, of course, mean its image under the structure map from lambda to R because R is a lambda algebra. Okay. Intuitively, I think of R here as functions on some base pointed space, and then MR is the functions vanishing at the base point. So then T star R is the quotient of MR by the higher order terms of these functions. That is, we're linearizing. We're isolating the linear parts like derivatives should do, like tangent spaces should do. Okay. Note that T star R is naturally an R mod MR or lambda mod M lambda module. That is, it's a K vector space. The way I think about this is scalars vanish, scalars times vanishing functions should still vanish. Okay. And they also shouldn't, if you multiply a scalar times a linearized function, it should still be linearized. Okay. So what's the Zariski tangent space? It's the dual K vector space to T star R. So it's called TR, and it's the K maps from the cotangent space to K. Since R is Noetherian, T star R is a finite dimensional K vector space. And so TR is the natural K dual from vector space theory. Okay. So let's consider the functor D sub R from C lambda to sets given by B maps to D sub R of B. What is D sub R of B? It's the C hat sub lambda maps from R to B. So this functor is represented by R, essentially by definition. Okay. And so what I'll do is I'll invoke the lambda algebra known as the ring of dual numbers, K adjoin epsilon, which is defined by the relation epsilon squared equals 0. This is a two-dimensional K vector space itself because it is K direct sum epsilon times K, where the first component in the direct sum is generated by the unity of the ring, and the second is just the maximal ideal. Okay, so I would check out Hartshorne or Vakil's book for more details about this. The main result is there's a natural isomorphism of K vector spaces between the following two sets. So the K vector space maps from the cotangent space to K, in other words, the Zariski tangent space, to the set of lambda algebra maps from R to K adjoin epsilon, the ring of dual numbers. So this allows you to think of the tangent space sort of purely ring theoretically. Okay, so this is a well-known result in introductory scheme theory. You can see Cornell, Silverman, Stevens, page 271. You can see Vakil's Rising Sea book. You can see Hartshorne's book. You can see all kinds of places for this. Okay, but this proposition tells me something interesting. It shows me that there's actually a functorial interpretation of the Zariski tangent space, because T sub R is isomorphic to D sub R of K bracket epsilon, essentially by the proposition, right? But that prompts the following definition. Let D from C lambda to sets now be any covariant functor such that D of K is a one element set, like we had up D sub R of K was one element set up here. The Zariski tangent space of the functor D, which will be a K vector space that we'll have to prove, and we'll do that today, written T sub D is, well, what should it be? It should be D of K bracket epsilon, right? Because T sub R was isomorphic to D sub R of K bracket epsilon in our specific case, okay? So is this a vector space? That's the question. So is this a Zariski tangent space here, D of K bracket epsilon, actually a vector space, or else this doesn't really make sense, right? It is. I just have to tell you what the scalar multiplication by K is and what addition is. Scalar multiplication by K on T sub D is given as follows. Note that the lambda algebra endomorphisms on the ring of dual numbers, this acts on TD, essentially just by the functoriality of D. So I'll let you work that out. Okay, and there's a natural ring homomorphism, which is actually an isomorphism between K and this endomorphism group. Okay, and what is the isomorphism? It sends A and K to what we'll call alpha sub A. And now alpha sub A is supposed to be a lambda algebra map on the dual numbers. So what does it do? Yeah, well, remember, K bracket epsilon breaks down into K direct sum epsilon times K. So I just have to tell you what alpha sub A does to X direct sum Y times epsilon, right? For X and Y and K. And what it does is it just maps it to X direct sum A times Y times epsilon. Okay, so this turns out to be an isomorphism of rings. Okay, so there you go. There you have a scalar multiplication then, because now you have an endomorphism ring action on T sub D, but endomorphism ring is isomorphic to K, so you have a K action on D, but a K action on D is just the same thing as a scalar multiplication, right? So now where does addition come from? And I guess you have to make sure addition and scalar multiplication actually interact correctly here, but that's not hard to do. So the plus map is pretty easy to define. Let's define the K-algebra map plus as follows. So it should be a map on the dual numbers, right? So it should be a map from dual numbers cross dual numbers over K to dual numbers, and we'll call that map plus. What should it do? Well, again, everything in K bracket epsilon looks like something in K plus something in K times epsilon. So I have to tell you what this map does to x direct sum y1 times epsilon, comma x direct sum y2 times epsilon. And it does what you think it should do. It kind of adds in the second component. So it sends this to x direct sum y1 plus y2 epsilon. Okay, so to continue, you're going to need an additional assumption on the functor d, which is called the T sub k, or the tangent space hypothesis. Okay, so here's the hypothesis. The map from D of dual numbers cross dual numbers to, the map H from D of dual numbers cross dual numbers to D of dual numbers cross D of dual numbers, discussed before in the previous video. So there's a natural map here, essentially by the universal property of fiber products. This should be a bijection. So that's the tangent space hypothesis. Here's why you need that hypothesis. If D has the tangent space hypothesis, you can actually continue and make this plus operation here. You can use that to define an addition operation on the Zariski tangent space, the Functorial Zariski tangent space, as follows. It's just a composition map. So what you do is you start with D of K bracket epsilon across D of K bracket epsilon. That's what you want an addition law on, right? You apply the H inverse map, which exists because we're assuming H is a bijection, to give you a bijection from D of dual numbers cross dual numbers. Now you already have a plus map from dual numbers cross dual numbers to dual numbers, right? And D is a functor and it's covariant. So there should be a D of plus map from D of dual numbers cross dual numbers to D of dual numbers. So now we have a map, now we have an addition law on the Zariski tangent space. Okay, so this is just a map T sub D cross T sub D to T sub D. Okay, and you can check all the vector space axioms are satisfied and all that. All right, so we're going to start to see next video how the Zariski tangent space is going to come into play and help us begin to develop some more deformation theory. So I'll see you then. Thanks for watching.